Afternoon. My talk is about designing an algorithm for constraint optimization problem over directed networks. For my talk, first we'll introduce the distributed constraint optimization problem. Then we will look at the current research status on this problem. Then we introduce the designed algorithm to solve this constraint optimization problem. Then we will show you some simulations to see how efficient of our algorithm to handle those problems. For the distributed constraint optimization problem, in the beginning, I just want to introduce you a very common problem from computer science. In fact, from machine learning. So linear support vector machine, given training samples x1, y1 to xn, yn, where the yi are either 1 or -1, each indicating the class to which the point xi belongs, finding the optimal classifier, the maximum margin hyperplane that divides the group of points xi for which yi is 1 from the group of points for which yi is -1. Samples on the margin are classified. The support vectors as minimize w, and under the condition yi times wt xi minus b bigger than or equal to 1 for training data linearly separated. So now, for the cases in which the data are not nearly separable, the loss function is introduced as the following function. The function is 0 when xi lies on the correct side of the margin. For data on the wrong side of the margin, the function's value is proportionally to the distance from the margin. So basically, converted to the following mathematical problem. So we can convert this problem as the following optimization problem, where x is a global decision vector, fi is a local convex, not necessarily differentiable, objective function of agent I, and xi is the intersection of xij, which is an intersection of a finite collection of simple convex sets. Gi is a vector of convex function accessed by agent I. Basically, many problems from engineering, computer science can be transformed to distributed convex optimization problems on multi-agent networks in which all agents work together to minimize a shared cost function in the circumstance of various constraints. In the algorithm, an agent only communicates with its neighbors the communication architecture can be formulated as a network. We net GVE indicates an unbalanced direct network that collects M agents. The set of agents is represented by V, and the set of edge between agents is denoted by E. Suppose that self-loops do not exist in the network. Basic means II does not in E. If agent I can directly send information to agent J, then we get Ij is in E. The weighted matrix is a non-negative matrix such that Wij is positive if Ji is in E, and Wij is zero otherwise. The set of agents with which agent I can directly acquire information is the in-neighbors of agent I, which is represented by this. Now, if we satisfy this condition, we call the network is balanced, otherwise is unbalanced. Suppose that only one agent at each time is randomly selected to broadcast its information to out neighbors over an unbalanced directed network, where each interaction link in the network is subject to possible link failures. Because of that, at each time, the interaction link will be active or inactive with the probabilities Pij and 1 minus Pij, respectively. The associated agents will be weakened when the link is activated. The implementation of distributed algorithms mostly relies on the well-studied consensus theory techniques because it allows agents to perform local operation and to share limited information with their neighbors to achieve global results. Nedick and Azadagna proposed a distributed subgradient descent algorithm to achieve consensus among agents and using subgradients to minimize the sum of all local objective functions collaboratively. After that, many algorithms were developed for undirected or directed unbalanced networks. The so-called surplus-based methods were proposed in the following reference to handle directed graph, but it's fixed. Nedick and Arshevsky proposed an algorithm incorporating push-sum protocol into distributed subgradient to deal with the underlying graph in time-varying and unbalanced direct network. Unfortunately, this idea cannot be applied to constrained optimization problems. You and others combined the distributed subgradient method with Haryak's random projection method and proposed a simple distributed algorithm to solve the optimization problem with local convex inequality constraints over unbalanced direct network. Xie and others proposed a distributed random fixed projection algorithm over time-varying unbalanced direct networks. This method addresses unbalancedness by means of an epigraph form of the objective function. However, the update of the algorithm is in a synchronous fashion, and the step size of the algorithm is constrained. Why asynchronous? An agent has to work based on its own clock, steering the algorithm to be executed in an asynchronous manner. Besides, networks are susceptible to certain possible link failure. Netcat designed an asynchronous broadcast-based algorithm to deal with scenarios where interactions over the whole network were subjected to possible link failures, and updates were asynchronous for undirected communication network and unconstrained optimization problem. In the following, we introduce the fully distributed and asynchronous broadcast algorithm to solve the constrained optimization problem over directed networks. Epigraph form of constrained optimization to deal with the unbalancedness of the networks. We converted the optimization problem to epigraph form. The epigraph of f of x we defined as this. Minimizing the convex function is equivalent to minimizing the linear function in a convex set. So we can convert it to this optimization problem. So the optimization problem is a linear function. So looks that's simple. Now with some constraints. So we want to find some algorithms to discover or find the solution to this optimization problem. Now, we want to introduce the broadcast-based optimization algorithm. What's this? We suppose that only one agent in the network broadcasts its own information at a certain time k. Assuming ik is the index of the agent that broadcasts information at time k. Because of possible link failures, only subset jk of the out neighbors receives the broadcast information. We use xjk, tjk are two local estimates for agent j at time k. They distribute or synchronous broadcast-based algorithm is divided into two steps. Step 1, updates of the intermediate state variables. Step 2, the dynamical averaging consensus process for variables. Step 1, at time k, agent j is in ik and jk. Update intermediate state vectors as this. Now, omega is a random variable drawn from the integer set at this time. Step 2, we want to update x, jk, and t, ik using the dynamical averaging consensus process. WIK is a weight from broadcast agent IK to agent I at time K. From agent I, do not acquire information from IK, do not update their states. Once all agents reach an agreement, or basically consensus, the state vectors asymptotically converge to a feasible point. Now, this is our algorithm we design. So first, we initialization of those states or parameters. Then we set start from 0. The local information will be exchanged, and the local variables updates through this designs. Then we need to update it through dynamic averaging consensus these two variables for XIK and TIK. Besides, agent IK and I that do not acquire information from IK do not generate their states. So basically, no change for this. Then we just repeat this process until a predefined stopping rule is satisfied. To design an efficient algorithm, we need some assumptions. Suppose that W is the weighted matrix of network G. The unbalanced direct network is strongly corrected, and the possible linkage failure for this in the network is independent and identical distributions. That is, the link is functioning independent of other links with probability. The weight Wij is positive when Ji is in the edge, and the diagonal entries of W are positive. Basically, this means this can guarantee each agent's information reaches other agents frequently enough through broadcast strategy. Assumption 2, the two sequences, omega, identical and independent distributions, and are uniformly distributed over from 1 to 2 to 3 to tau j. And for the set 1 to uj for any j respectively, this is uniformly distributed. In addition, the sequences are respectively independent of the index j. Another assumption, that's about boundedness of subgradients and solvability. This from the paper published by HB Transactions on Automatic Control, written by Dr. Xie and others, with title Distributed Convex Optimization with Inequality Constraints over Time Varying and Balanced Diagraphies. So we call this boundedness of gradients and solvability. First, the subgradients of objective functions fi and constraint functions ji are uniformly bounded over this set. Another condition, the optimization problem is feasible and possess a non-empty optimal solution set. Another assumption, this is a finite constraint such that for all of theta in this set, this distance satisfies this condition. Now, this condition is coming from the paper published in Proceedings of the 2013 IEEE Global Conference on Signal and Information Processing. With those assumptions, we have the following convergence result. Suppose that the optimization problem exists in non-empty optimal set X star, and assumptions, all of the assumptions we just talked are satisfied. Then the sequence X, IK, TIK converges almost surely to the optimal solution. Sorry. Here's the assumptions. We can get the states, intermediate states for X and T. We are converging almost surely to the optimal solution. They rigorously modify the result is complicated. So here, of course, I don't look at this part. You can refer to our paper. This result is very interesting, and it solves lots of problems which couldn't handle before. Now we just look at 3 problems. First, for vicinity location problem, the corresponding convex optimization problem is given in the paper entitled Improved Approximation Algorithms for the Uncapacitated Vicinity Location Problem. This paper published in Mathematical Program in 2004 by Doctors Chudak and Schmeiers. So this problem is to minimize the function f of x. F of x is defined as the sum of x minus bi times a parameter ai. So x minus bi, this one basically that's the distance for the chosen location with given locations. Now this of course with some constraints. For example, the location of the chosen one, the distance with one group locations, suppose say I1 should be cannot bigger than Li1. Now the distance between the chosen location and the given some locations cannot be bigger than Li2. In this simulation, we just choose 5 agents. So the 5 agents collected by an unbalanced direct network as a figure here. So we represent this as a graph, okay? Now the step size, we pick as 1 over gamma jk. Gamma jk represents the number of updates performed by agent I until time k. Now we just look at the simulation results. We run this optimization using 3 algorithms, okay? Of course, the red one, the solid line, that's the one implemented by the algorithm we proposed here. Now the blue one, this method, the algorithm from the reference below, the first reference. Now the paper written by Doctors Xie, You, Temple, Song, and Wu. They wrote in this paper before 2018. Now this paper published in IEEE Transactions on Automatic Control with title Distribute Convex Optimization with Inequality Constraints over time varying unbalanced digraphs. Now the other one is from the paper published in IEEE Transactions on Automatic Control in 2017 by Doctors Nortanikona and Nortastefano, with a paper entitled Synchronous Distribute Optimization via Randomized and Proximal Gradient. Now, for the one, the algorithm from the paper published in 2017 in the second reference. Since this one cannot be applied to the link may be subject to failure. So that's why it can never convert it to the optimal solution. Second simulation. Before that, I want to show you another simulation result. So the blue line, that's the one from our proposed algorithm. The red one, that's the algorithm implement from the reference below, basically written by Dr. Xie Yu and Temple, Dr. Song, and Dr. Wu. Now we can see our algorithm approaching to the optimal solution very quickly and very good. Now we consider the second simulation result. We consider the following optimization problem. So minimize the function f of x defined as the sum of the distance. So by ij x delta ij. Now for all of the phi ij is in delta I. Meanwhile, this should be satisfy g of I always smaller or equal to 0. This is one constraint. The other one, x should be in the intersection of xi. I is from 1 to m. Where phi ij is the Huber penalty function used to estimate the influence of outliers and defined by the following function, where delta ij is a observation. In this simulation, we just let m is 100. So there are 100 agents. The notation n rho sigma denotes a normal distribution, with rho is the mean value and sigma is the covariance. The Huber penalty function is implemented by 100 measurements perturbed by additive function. With the Gaussian noise, the first 90 measurements denoted by phi ij, j is from 1 to 90, are said to be identical and independent distribution with center is 1, and the covariance is 1. While there remain the 10 distributions, we denoted as phi j when j is 91 to 100, are said to be 10 independent and identical distributions. The collection of phi ij is represented by delta phi ij. J is from 1 to infinity. Now the experiment generates a strongly corrected and unbalanced directed network with M100 agents using nearest neighbor rules. Now, for this simulation results, look at here. Horizontally, that's the iteration time. Now for the blue one, that's the difference from internet. So that's clearly we can see this 3 will approach to the equilibrium points, but I will look at the other. Now this one you can see when the failure rate, the link failure rate is smaller, like the red one and the green one, they approach to the optimal solution faster. Now, for the final experiment, the last simulation I present, it describes the scalability of the proposed algorithm and other methods to the directed networks and present the simulation results for a special unbalanced directed network we depict in the graph below. For this one, we suppose that the Huber penalty function in the example 2 is independent by 10 measurements in which are said to be identical independent distribution. Due to the push sum method can only be applied to the distributed and constrained optimization problem. Here, we remove the inequality constraints and the constraints that set in the operation for compression. Now the following table, we can see the number of now the number of iterations required to reach the approximate minimum value for the proposed algorithm and the 2 kinds of push sum methods. We compare this. when we do the comparison, since the push sum method cannot apply to the constrained optimization problem, it can only apply to the distributed unconstrained optimization problem. So here, when we do the comparison, we need to remove the inequality constraints and the constraints set in the optimization problem for comparison. Okay. Now we can see for the agents is 10, 20, 30, 40, all algorithm, the iterate time increase much slower compared or synchronous push sum. Of course, push sum is running faster to our algorithm. However, for the push sum, as I mentioned, cannot apply to the constrained optimization problem. Finally, I just want to summarize my talk. So I want to mention the contribution we make. First, a very outstanding distributed or synchronous broadcast-based random projection algorithm to solve distributed convex constraint optimization problem over an unbalanced directed network is developed and analyzed in this article. Compared with the recent work, the proposed algorithm figures out the optimization problems based on broadcast model and focus on the uncertainty of agent interactions triggered by possible link failures. This is inevitable in plenty of practical applications such as sensors, power, and wireless communication networks. Second, in comparison with the existing work, the proposed algorithm can be applied to the distributed optimization problem with both different inequality constraints and non-identical constraint sets, even over unbalanced directed networks. Moreover, the epigraph form of the constraint optimization problem is adopted in this article to solve the unbalancedness induced by directed networks from a new perspective, which is a distinctive method and has not yet been studied in. Third, the proposed algorithm is updated asynchronously, and it admits to employ and coordinate the step size for all of the agents in comparison with the most existing methods in 1 and 2. Moreover, the proposed algorithm also adopts the Parniak's random projection method, which is subject to the distributed existing algorithm for constraint optimization problem that utilize Euclidean projection operators. Final contribution we make: the convergence property of the proposed optimization algorithm is fully analyzed, which provides insight of broadcast based asynchronous strategies for distributed constraint optimization problems over unbalanced directed networks, and further considers more realistic scenarios than existing work. Finally, I want to share with you about the future work in this direction. In our point of view, this work, even though it's good, but cannot apply to time-varying networks. That's a shortcoming. And the networks with the noise, quantization effects, and communication delays, we have not considered those effects in. So it would be interesting and very important to extend the algorithm and these theoretical properties developed here to the case of time-varying and balanced directed networks with the consideration of possible link failures, quantization effects, and communication delays. So basically, I complete my talk with this. I'd like to thank all of my collaborators, especially Professor Huaqin Li from Southwest University. Thank you all. Thanks to Qatar University.